So as I mentioned in class, it didn't seem like we'd have time to fully draw and sketch out all of the quadric surfaces using traces. So we did 2 in class. I'm going to kind of talk about the idea and the process, and then I'm going to do the other 4 here now. As I've said, this isn't something that I would ask you to do on an exam. This is just a way that we can use information that we extract from the equation of the quadric surface to visualize what it would look like, which is actually really cool. So again, to reiterate, the idea is that we're starting with the equation, visualizing it using 2 main pieces of information. The first would be the intersections with the XZ and YZ planes, and then the intersections of the surface with the Z is equal to K plane as we let K vary, just as some real number. So I guess really this is Z is equal to K planes, because we're just taking a ton of different slices throughout the shape and seeing what the different cross sections that we get look like. And so often what will happen is that we'll say that the quadric surface is generated by the curves from that second step, while the edges or vertices of those curves lie on the traces from the first step. So the first example that we did was the ellipsoid. Maybe I'll write that up here too, just so that it's kind of complete. The ellipsoid we found has coordinate plane traces given by 2 ellipses. So that's our E1 and E2 for this example. Then when we looked at intersections with the plane Z is equal to K, so that's if we're kind of just taking these slices this way, moving up the shape, orthogonal to the Z axis, we find that the equation that we get is the equation of an ellipse as long as there's the condition on K that keeps it between -3 and 3. Outside of that, then you get an equation where you've got something positive on the left-hand side and negative on the right-hand side, which makes no sense, so we don't get any surface. That's why our surface stays between the Z values of -3 and 3. And so here we get these ellipse EKs, so the ellipses that generate our surface, and this is kind of our summary sentence of what the ellipsoid is. It's generated by ellipses that move parallel to the XY plane, while their vertices lie on the ellipses E1 and E2. And this one, we've said that it's centered on the Z axis, but you could actually do this from scratch as if it's centered elsewhere, and you would still get the same shape. Just because the ellipsoid is just all ellipses everywhere, all the way down. And if you'd like to get a closer look at this shape, you can use this Desmos link to get there. The second shape that we looked at, or the second quadric surface, was this one. This is the elliptic paraboloid. I'll write that here too, just so that we have that handy up here. It's called the elliptic paraboloid because it's generated by ellipses. So this would be one of the ellipses EK. So every time we kind of take a cross section perpendicular to the Z axis, we would get an ellipse. But the whole shape is framed by these 2 parabolas, P1, P2, hence paraboloid. And so this is how we figured that all out. And again, a Desmos link. Now, unlike the ellipsoid, the elliptic paraboloid does have the potential of changing the symmetry. Like this one is opening upwards, but it could have been opening up along the x-axis or along the y-axis. And so these changes, we can change it as saying where it's centered or like what the axis of symmetry is. Axis of symmetry, I guess, doesn't always perfectly apply, but that's kind of just the way you can think of it. So we can say like, or centered on, that's kind of the idea. So for instance, if we look at this equation, y is equal to x squared plus z squared, here y is the one that isn't squared. So as we let x or z be 0, we see that we get parabolas holding it in. And then as we set y is equal to k, we would get ellipses moving on up like that. And so it's generated by ellipses. As well, the ellipsoid also didn't have to be centered at the origin. The one we did just was. So similarly, we could shift kind of the vertex, whatever the starting point is of our elliptic paraboloid elsewhere. That would be fine, just by adjusting it, like with that little subtraction, that kind of thing. So those are our first two shapes. Now let's get into the last four. First, we have this one with the equation z is equal to x squared minus y squared. We're going to follow those same two steps as before. First, we're going to look at our traces, setting either y is equal to 0 or x equal to 0. If we set x equal to 0 in that equation, we get that z is negative y squared. That's a parabola. We'll call it P1. That negative means that it's opening downwards. Like in the negative z direction, right? Then when y is 0, we get that z is equal to x squared. That's the equation of another parabola. We'll call that one P2, and we can think of that one as opening upward. It's a positive coefficient in front of the x squared. Upwards, upward, whatever. Okay, and then now that we've got that, we've got our two parabolas. And maybe I'll sketch them kind of just on top of the finished shape here to give you a sense of what's going on. So P1, that one is entirely in terms of y. So it lies on the YZ plane. You can kind of think of it as kind of going like this. This would be our P1, pointing downwards, while P2 just kind of rests like this. So that kind of crest of the hill of that saddle point there, that gives us P2. All right, okay, then our second step, we're looking at our intersections with the plane Z is equal to K. Intersections here, let's say we've got K, then instead of Z, if K is equal to x squared minus y squared, then we get three types of hyperbola. And it all depends on if K is positive or negative or 0. So if we get three different types of hyperbola, depending on the value of K, this implies different cross-sections if we're taking them above, below, or on the XY plane. Okay, so what are those three different types then? What can we see? First, if K is positive, we get the hyperbola shaped with a kind of like horizontal reaching, I guess. I'm not sure what the technical term is, but this is what we're talking about. X squared plus, or x squared minus y squared, sorry, for this one, is equal to K. I guess in all cases, we're going to say it's the hyperbola HK. So for this one, that's our HK. And if we were to add that on top of the existing graphs here, that would be an wrong color. That would be HK like this. So it's opening up along the x-axis. It's maybe kind of like that for K positive. If we were to draw it on top of this one, it's like that. Then for K negative, we'll get ones that are opening up and down essentially. Let's say we use orange for that. we get this kind of hyperbola. Again, with the same equation, it's still x squared minus y squared is equal to k. It's just that k happens to be negative. And so then if I were to place that on top of this graph, so when k is negative, that means we're looking below the xy plane. And that's how we get something like these guys. So maybe this here, there would be one reaching out on the other side. It's just not really, not really feasible to draw directly on here. Same idea for this one. Got that, and then there's another one on this side. Okay, so those are the two kind of big cases. We've also got the situation where we could just have if k is equal to 0. Well, if k is equal to 0, the hyperbola is actually a pair of lines. This is called the degenerate case. Again, this is something that you would have covered in Math 20 if you took it 15 or more years ago. They talked about this. So if you have x squared minus y squared is equal to 0, we factor that using difference of squares as x minus y times x plus y is equal to 0. So we get two lines really. We get the line y is equal to x, y is equal to negative x. So in this case, I guess our hyperbola is actually just a pair of straight lines. Let's use, I'm going to change this purple. That one's too bright. I guess that's one thing about doing these outside of class time is I have more time to fiddle like this. Okay, so that's the pair of lines we're looking at. I guess I could have done each of them a different color, but I think we'll be okay if we just do them the same. And those, again, that's when k is equal to 0. So that's directly the intersection with the xy plane. So we get like those two here for k is equal to 0. These ones are easy to identify just because of the way that Desmos does that kind of transparency. So that's convenient. And then there would be ones on the other side. I guess I should also add that's k less than 0. Yeah. Hopefully, as I've been adding this all kind of makes sense together. If I were to try to sketch from scratch on this pair of axes, I guess not pair, this triplet of axes, we can start off with our P1 and P2. P1 we know was going downwards, and it was just z is equal to y squared. So not like overly stretched in any way. So we could say P1 is kind of like that. P2 is opening upwards quite nicely. Again, this is three-dimensional. It's kind of hard to sketch, but we're doing our best. This is just to kind of help with seeing the point, or like kind of the general shape of what's going on. We've got these lines extending out. And then if I draw some of these hyperbolas, we can kind of see how their edges lie on the parabolas. So we're kind of moving upwards with the positive k value cross sections lying on P2. And then the negative k value cross sections are lying on P1, kind of opening outwards. That's kind of interesting. It's kind of like that. And then these ones will go like that as well. But, oh, that looks like it's going up. I'm not satisfied with that. If I were to try to actually just draw it as it is, and that kind of saddle point is a weird shape. I'm not sure. You know what? This is good enough. Like I said, maybe I'll take some extra time outside of this video and see if I can do a better sketch. But now we've got to write our little summary sentence. we know that the hyperbolic paraboloid is what we're looking at here. The hyperbolic part comes from when we're looking at when z is equal to k, and the paraboloid part comes from the xz, yz traces. This shape is generated by a hyperbola we can call hk that moves in a plane parallel to the xy plane. With vertices on parabolas P1 and P2. So that's our hyperbolic paraboloid. I'll write it over here as well. As well, if you'd like to pull up the Desmos link to kind of get a look at it, I think this was a good one to kind of zoom in on and see the kind of things you can get. As with the other shapes, we can switch around the variables to get a different kind of symmetry or where we're centered. And then we could also even shift around, right? So it's not centered at kind of the origin. But you know, we're just looking at initial examples to get an idea of how it could generalize. All right, now we've got another quadric surface to look at. We're going to start again with our traces with the coordinate planes. So we'll see what happens when x is 0 or y is 0. If x is 0, we get y squared minus z squared is equal to 1. This is a hyperbola. We're going to call it the hyperbola h1. And then when y is 0, we get x squared minus z squared is equal to 1, which is another hyperbola. Hyperbola h2. If we were to place h1 and h2 on this surface already to see what's happening, I'll do another sketch from scratch further down, but this is just to kind of pair things up. H1 we know is in x is equal to 0 plane, so it's on the yz plane, so we can draw it like this. This is h1. Maybe that I should do dotted line. Also h1. There we go. And then h2 is the one that's going to be in the y is equal to 0, so like the xz plane. Let's put that here. Okay, so there's our h2. Now we can get our second step information. So we know that whatever shapes we get from the second step will be what generates our surface as the vertices lie on these two hyperbolas. So if we look at the z is equal to k cross sections, and see what we get. Just setting z is equal to k as before, we get x squared plus y squared minus z squared is equal to 1. So here we have something that I'm going to just rearrange. So it's like x squared, there we go. X squared plus y squared is equal to 1. Oh, shoot, sorry, I put z squared there. I meant k squared. Okay, so then we get 1 plus k squared. And both sides of this are always positive. So that means that there's going to be no limitations on k. if we were to rearrange this and see what kind of equation this is and what our cross sections actually are, we could divide both sides by 1 plus k squared. And this is an ellipse. We call this the ellipse EK. If I were to, let's say, add these to the surface that we've got here, looks like this. And, you know, we get infinitely many of these. These are what are generating our shape. We've just got a bunch of different ellipses stacked on top of each other. In this particular case, this one is actually a circle because we have actually the same coefficient under both the x squared and the y squared. In fact, even just from this step, we can see, this step here, we can see that it's a circle. Wow. Of radius root 1 plus k squared. So, okay, actually a circle of radius root 1 plus k squared, and it's defined for all k real numbers, which is awesome. And that's why we get this shape going forever in both up and down. There's no gaps in it. And that's all we need. This is enough to talk about the hyperboloid with one sheet. So hyperboloid, the thing that's oloid, I guess is the way to think about it, is what your coordinate traces are. So your frame for the shape. So the hyperboloid with one sheet. I'm gonna write that up here too. With one sheet. One sheet because it's kind of one continuous piece of material. It is the surface generated by the ellipse EK that moves parallel to the XY plane. Having vertices on the hyperbolas h1 and h2. Yeah. So if I were to kind of start from scratch on a set of axes, maybe I'll copy and paste one of the blank ones I had up here. Oh, why is it not going behind? Okay. So we know that we get all these little EKs. We even have one when k is equal to 0. E0 would be the unit circle. Isn't that interesting? I guess we can draw that even. And then let's get our two types of hyperbole. Hyperbole? I don't know. Down. We had h1 is the one on the YZ plane. And then h2. And then basically we're just going to see the shape grow bigger as we move up and down. Big hourglass. Nice. And as with the others, I've got the different forms here depending on where we're centered. If you want to identify it just looking at the equation, hyperboloids, we've always got everything squared, a 1 on the other side, and the axis, or where we're centered, is the variable that has a negative coefficient. So ours had a negative in front of the z. And I would recommend checking out that Desmos link. This is that z is equal to k plane, moving it up and down. Okay, then we're on to our last two surfaces. For this one, we've got the equation negative x squared minus y squared plus z squared over 4. And let's just go about those same two steps. First, let's see what happens when x is 0 and y is 0. X is 0 gives us negative y squared plus z squared over 4 is equal to 1. That is a hyperbola. And then when y is 0, we get kind of the same hyperbola, really, except that it's x instead of y. We'll call that one h2. If I were to kind of add these to the existing shape, we have something very similar to that last question, actually. Let's say, so for h1, it's the one on the y z plane. And then h2, let's use orange, I guess. That one will be the one on the xz plane. So it's reaching outwards like that. Okay, so there we go. Now, the thing that actually changes between the hyperboloid of one sheet and two sheets is something that we see when we set z is equal to k. Setting z is equal to k for this one, get negative x squared minus y squared plus k squared over 4 is equal to 1. And now we're going to rearrange this equation so we get to the point where we can kind of say something about things being positive or negative, get some kind of limitation. If I move like things to the other side, multiply by -1, whatever, rearrange, we'll end up with x squared plus y squared is equal to 1 minus, no, it's actually k squared over 4 minus 1. Yeah, because that's like if I move the k squared over 4 to the right-hand side now, and then I just multiplied everything by -1. Yes, that's right. Okay, so this left-hand side will always be positive. It's two squared things added together. However, on the right-hand side, we could have that be positive, but we could also have it be negative. So what that means is that we only have a cross-section, meaning the surface only exists at all, if this k squared over 4 minus 1 is also positive. So what does that mean then? What does that mean for k? If k squared over 4 minus 1 is greater than or equal to 0, that means k squared is greater than or equal to 4. In this case, that means k is either less than -2, there we go, or k is greater than 2, which we could just write as k is between -infinity and -2, or from 2 to infinity. And that means between those two values, that -2 and 2, we have no cross sections. And so no surface at all. For k between -2 and 2, that's how we get that gap. If I were to actually say what that cross-section is, so when we do have k between -infinity and -2 and then 2 to infinity, we get an ellipse. This one we would just divide both sides by that k squared over 4 minus 1. So this is the equation. I don't have that in it. Okay, k squared over 4 minus 1 plus y squared over k squared over 4 minus 1 is equal to 1. I guess for that one, I'm going to just change these to round brackets. Yeah, because if we have that k is equal to plus or minus 2, we actually get 0. We couldn't divide by 0. We get s squared plus y squared is equal to 0. That means x and y would both be 0, and that's when we get the points 0, 0, 2, and 0, 0, negative 2. If I were to then place this new information onto the existing surface, this could be one of our EKs. And then this last point we get below the xy plane is 0, 0, negative 2. And then this first one we get is 0, 0, 2. And then it just grows outwards from there. And that's the hyperboloid of two sheets, two distinct pieces of material is the way you can think of that. So, as our kind of summary sentence, and I'll also write actually up here, is this hyperboloid of two sheets. So, we say the hyperboloid with two sheets is the surface generated by the ellipse EK that moves parallel to the xy plane having vertices on the hyperbolas h1 and h2. Here only, in this example for absolute value of k greater than or equal to 2, but certainly depending on some of our coefficients, we could have had something slightly different. This is what we get if we're centered elsewhere. And we can see two sheets, we have two things that are negative. And that's kind of the pattern that we can pick up on. And here I've got that Desmos graph. And so you can see here, when we have k between the two sheets, we don't have any cross sections at all. We need to move it up to get the Ks, the EKs. Okay, and then now we're on to our very last quadric surface. Here we've got the equation z squared is equal to 4x squared plus y squared. Same steps as before for our traces. Let's see what happens when x is 0. Well, x is 0 gives us z squared is equal to y squared. This we're going to rewrite as z squared minus y squared is equal to 0, which we can then also rewrite as z minus y times z plus y is equal to 0. And so this tells us that the yz trace is in fact the two lines in the yz plane. The lines are, we're going to call them L1, the line y is equal to z, and L2, the line y is equal to negative z. So if I were to place these on our current surface already pictured, let's see, y is equal to z, that would be this one here. This is L1. L2, I'm going to do This is L2. And then we'll get something similar for the other traces on the XZ plane. All right, yes, yeah, the XZ trace. For this one, we get z squared is equal to 4x squared. This one, after some rearranging, I'm just going to skip ahead to the factored form. We get z minus 2x times z plus 2x is 0. So the xz trace is the two lines in the xz plane. We'll call these L3 and L4, and we get them kind of the same way. L3 would be the line z is equal to 2x, and L4 will be the line z is equal to negative 2x. So if I put these also on the surface we've got here, I know this, like, we're not like actually kind of sketching, it's just that I feel like this is an easier way to see where these traces come from, and then we put it together as a sketch on the end. So that's L3. For L4, that one will be like this. Now, I had initially tried to do these using Desmos, but like I didn't, at the time when I generated these, I didn't know how to do it just as a line, so it gave me these big planes. So maybe this isn't very useful. But think of it as just these 4 lines that we have, again, kind of creating our frame to hold everything in. Then, finally, we can look at the z is equal to k cross sections. For this, if we have k squared is equal to 4x squared plus y squared, we have both sides greater than or equal to 0. So it's always going to be possible to satisfy it for any value of k. If k is specifically 0, x and y will have to be 0. And we get the cross section is just the point 0, 0, 0. So we know that we kind of shrinked all the way down to the origin. But then if k is not equal to 0, we can rearrange that equation and we get it as 1 is equal to 4x squared over k squared plus y squared over k squared, which is an ellipse. EK. So we can put one of those down here. You can also rewrite this equation if you want it kind of a bit more obvious. It's x squared over k squared over 4 plus y squared over k squared is equal to 1. So this is a cone. The fact that we've got lines holding it in makes it a cone. And so if we were to then write our little summary sentence on what a cone is, we can say the cone is the surface generated. So it's generated by ellipses. Hopefully you're already kind of finishing that sentence in your head. Generated by the ellipse EK that moves parallel to the XY plane, because again, we're kind of just stacking them up vertically centered about the z-axis. To the XY plane, having vertices on those 4 lines, L1, L2, L3, L4. Having vertices on the lines L1, L2, L3, L4. So that's our cone. That's the last of the 6 quadric surfaces. Again, I've got a Desmos link. Here's a summary of all the different equations for you to be able to recognize. And again, just a reminder, you can translate them or center them. You know, if we flip the variables around. I've also produced a flow chart to help you kind of classify the equations if this is just how your brain works. Maybe you're a flow chart brain like me, but maybe you're not. Maybe you want to do traces, whatever you'd like. So that's it then. That's the overview of all of the quadric surfaces and we get their traces. I'm sorry I wasn't able to find time to do it in class, but hopefully this was illuminating. Bye.